Hello students, and welcome to part 3 of our semester 1 final review. This review is all about Kepler's law, which is the current unit we are studying. In order to be successful, you actually have two pieces for this unit with two learning targets. So the first one is that you can use Kepler's first law to predict the elliptical orbits of planets. So using eccentricity to determine if a planet's orbit is more or less circular and use that to determine the shape. And then also we need to be able to use Kepler's second law to compare velocity at different points in the orbit. So identifying the relative speed based on the planet's position, and also using data to support the law of equal areas and to be able to explain what is happening at different places in the orbit. So we're going to start with Kepler's first law. Here you can see an image showing Kepler's first law. And we see a couple of things here. The first thing is that from Kepler's first law, we know that the shape of every orbit is an ellipse. And that is some kind of oval. And we can tell how much of an oval or how circular it is based on the eccentricity, okay? Closer to 0 is more circular, and closer to 1 is more elliptical or flatter or more oval. Those all are the same. So when we're talking about the shape of planets' orbits, we're looking at how much they are eccentric or how their eccentricity is. Because we know a couple of things. We know that the planets go around the sun, but it's not a perfect circle, it is actually an ellipse, which tells us also that the sun is not at the center. You can see the center of the orbit would be here, but the sun is off to the side over here, meaning that the sun is not actually at the center, the sun is a focus. Now this has to do with the way that gravity works and the way that the planets were formed, and so it's different for each planet where the sun is in the orbit. And so because of that fact, the eccentricity also is different. On Earth, we have a fairly circular orbit. Some planets have an orbit that has an eccentricity that's like 0.001. And so it's really, really circular. It's close, which is why a lot of the early observations of them being circles were almost right, but it's not exactly perfect. And there are other planets and objects that orbit with much more eccentric orbits, and those are more stretched out, flatter orbits, and there's times where it's really close to the sun and then times where it's way far away from the sun. So that, in a nutshell, is Kepler's first law, all about the shape of the planet's orbits. Next, we talked about Kepler's second law. And Kepler's second law has kind of two pieces that go with it. Because of Kepler's first law, because this orbit that you see here is an oval, and you can see that the planet, it's showing us Earth, is traveling around the sun. And because this is not a perfect circle and the sun is not at the center, there are going to be times in the orbit where the planet is closer to the sun. So notice here, on the left-hand side, the planet is closer to the sun. And here on the right side, it is farther from the sun. So that tells us that there are times where the planet is going to be traveling faster, and there are times where the planet is going to be traveling slower. But despite that fact, Kepler's second law tells us about equal areas. So we have a line here. Now this isn't a real line. There's not an actual rope connecting the Earth to the sun, but this is an imaginary line. And that line will cover the same area in the same amount of time. This is the law of equal areas. The law of equal areas. And this is basically saying, let me erase this arrow so I have some more space to write, that if the time, so t, we're going to say 1, is equal to t2, then A1, which is the area, is equal to A2. So the area of each planet's cover in space is going to be the same for the same period of time. Now we can also flip that and say the opposite. If A1 is equal to A2, then T1 is going to equal T2. So if they are covering the same area, if the planet covers the same area, then it is going to take it the same amount of time. So going backwards and forwards with that to understand. Now, even though the area that's covered might look like it's different sizes, they're actually going to be the same, but sometimes they're going to be a little bit longer and the planet's traveling slower, so it's not going to cover as much distance here versus when it's closer to the sun, and other times we'll see that it's actually going a little bit faster, and so it's closer to the sun, so it's kind of like our pizza analogy we saw in our pre-Zoom work. Thanks for watching.